we have a time, just quickly review the chapter 7 to the 13, and we are ready for your final exam, then we will have the winter break. Okay. Yes.
Excuse me, Professor, I think last class, on Monday, you mentioned chapter 8 to 13. Is it, so for final exam, is it 7 to 13 or
Yeah,
8?
so we cover only chapter 1 through 6, right? In the midterm exam.
1 through 7, I believe, in the midterm.
Deadlock was not in the midterm exam, right?
I thought we were.
No. So we covered only chapter 1 through 6 in the midterm exam. And it's just after the midterm exam, 7 to the 13, I think. Okay. So anyway, it's not comprehensive exam, so it's just after the first midterm exam. Okay. And there are several things that you need to check because the GA will not be available next week. So you need to check all your grading by the end of this week. So including project demo and any homework grading. So please check with the GA after the class, the rest of this week. And we will have the final exam on Monday. After the final exam, I'm not going to take care of any grading except the final exam. Okay, pretty much I will offer my office hour on Tuesday morning. Okay, I will let you know the exact time, and date should be the Tuesday. Then you can check your final exam sheet. That will be the last one. Then the afternoon, I will report your final grade to the registrar office. And so that will be done for the operating system in this semester. Okay. Any question regarding to the final exam and the other thing before we start the final lecture? Regarding to the final grade, so first I'm going to separate the undergraduate and graduate school. So it will be the different policy, different grading policy applied, and also don't pay attention to the percentile on Canvas. That's automatically generated by the Canvas. Okay, it's not mine. So for example, if a quiz is out of 100, it will be considered as the same weight as the midterm. So don't pay attention to the percentile on the final grade on Canvas. I will apply my own policy to the final grade, weighted final grade, weighted final score. Then based on that, I will decide the final grade. Then usually I do not apply the curve for each the item. Instead, after I got the final score, then the lower down the grading policy. Like the A is not 95 and above. So if your average is lower than the usual, then I will lower down the range of each grade. Okay, so that's my approach. So otherwise, half of the student will be failed. Okay. I know sometimes some of the works are a little bit tough, and I will adjust it. Mostly, I try to make the normal distribution, but sometimes but we will see. And I think pretty much that's the final. You will get the email, the Canvas message probably Monday evening, late evening after I finish all the grading. Okay, you will see your final grade also. I will try to my best to post your final grade, the final exam, and the final score, weighted score. Okay, so we will continue today's lecture for the page replacement. So for as we discussed before, most of the current operating system use a virtual machine due to the limitation of the memory, but also same time we have the more and more processes. So to keep the high degree of the programming on the computer, so we consider virtual machine. Virtual machine is the virtual memory, not virtual machine. Virtual memory means anyway, the CPU would like to read the information or instruction from the memory, but that memory should be a physical memory, right? Doesn't make sense to read the instruction or the data from the hard disk drive, which is too slow. There's a huge speed gap. But so we cannot increase the physical size of the memory. Instead, we pretend the all process are loaded into the memory. Okay, ideally. But we do not have the space, so we consider the logical memory, which means the program that you are going to execute running on the memory as all the memory. That is a virtual memory. Anyway, we have the limited space on the physical memory. We separate some part of the logical memory, which is not in the physical memory, but in the virtual memory. So that virtual memory space, we are going to use what? The persistent disk. So sometimes it's called the virtual memory space. Sometimes in Linux, it's called the swap space. So there will be definitely in and out. That is the page in and out, not the entire process. The in and out, that is the swap in and out. Long time ago, we used the swap in and out, but nowadays we use a page in and out. So that is the idea of the virtual memory. However, since we have still the limited the number of pages, so we need to decide if we cannot find the free frame, we need to decide. So if all the seats are taken, we need to decide one of the student kick out, then bring the new student to the seat. That is called the page replacement. At that time, which one will be the victim page? Depending on the decision algorithm, there are several approaches. Okay? As we have seen in the real cases, the page in and out happen a lot. Okay, that determines the performance of your system. So if you are going to manage the server or the Unix server, Linux server for your future job, so probably the most asked question is the system is slow. And first, you should have the processor to check the performance of your system. One of the important criteria is the page in and out. So to simulate the page replacement, we are going to use the two reference streams. The number indicate we simplify the problem that each page has only 1 byte of the data. So this is the data in the page. So 1, 2, 3, 4, and 1, 2, 5, 1, 2, 3, 4, 5, and so on. And another the data, which is the reference. So this is called the reference stream. So first algorithm is the first in, first out. When we decide the victim page, which one should be replaced, we consider all this one first. Okay, that is the first in, first out. The people algorithm. Do not confuse. This is along the time. So for example, in this case, we have only 3 page frames. The page frame means it's a physical memory. Okay, so we have only 3 pages on the physical memory. But we try to, CPU would try to read this data. Okay, where are they? Actually, the data is in the hard disk drive as it can be data file. It can be program. It doesn't matter here. Okay, so for example, the first time when CPU read 1, there's no data in the physical memory page frame. So this is our page frame. So there's no data. Probably page frame number is 0, 1, 2. That is different from that data. Okay, don't be confused. So I'm not going to indicate such a page frame number. There's from top to bottom. So 1, this is called the page fault. Page fault means if you cannot find the data in the page frame, physical memory, so you need to read such a data from where? Virtual memory. Okay. So for example, if this is the first time, probably that is in the hard disk drive. Then read the data, the 1, and bring into the page frame. So this is a page fault because you cannot read the data from the memory. So then, so on. 1, 2, 3. So erase the first sign. Is the 1, 2, 3 will be the page fault. So do not forget to counter the initial page fault. That is the reason when you start up your operating system, think about your old version of Windows system. It took time. to start. That is the problem of the Windows. So one of the reason is when your operating system start the kernel and everything, it will be most of them will be page fault. Okay, so that is a page fault and so on. So for example, when CPU try to read the data flow, okay, this is data flow, but there's no data flow. You need to decide one of them as a victim. So we will consider first first old one is the victim. Old one is definitely 1, so 1 will be replaced by the 4. So this is another page fault and so on. So for example, in this case, currently 512 on the physical the memory page frame, then we like to read 1. 1 is already there, so you don't have to page in and out. There's no page fault. You can just read the 1 from the page frame. Okay, so there's no page fault and so on. So you can count the number of the page fault, 9 page fault. In case you have the 4 page frame, so it's a bigger size the physical memory. So our expectation is the bigger size memory we have, the more page frame we have, the better performance like this one. Better performance means less page fault. Okay, this is our expectation. So when we check the same reference string with the full page frame, then 1, 2, 3, 4, those are the page fault, and the 1, 2 there, which is 1, 2 is not, and so on. Then if you count the number of page fault, it will be 10 page fault. So which one is the better performance? 9 page fault or 10 page fault? 9. Less page fault is better, which means in this case it's the abnormal case. It's non-usual case because this time even though it has 3, less the page frame it has, but better performance. This is called the belated anomaly that happen depending on the pattern of the reference string. So we will see the similar cases in the next slide. Not this one, after that, such cases. So you can practice the same algorithm with a different reference string. This is the first FIFO page replacement with a FIFO with a different reference string you can count. Okay. Definitely, I'm going to make the one question for this one. Just one time practice by yourself. Okay, that's pretty much enough. Yes.
Professor, regarding the final exam, is it all open questions or?
So we will talk about after we finish the lecture.
Okay, thank you.
So then, the next algorithm, that's what we did the last class. Today, we are going to see the several more page replacement algorithm. The next one is optimal algorithm. Optimal algorithm means, so what is the idea of the page replacement? Which one is better to keep? Will it be used or will not be used?
Most used.
Most used or the will be used, right? Anyway, the past is past, but in the future, we'd like to keep the page that will be used, reused again. That is the idea of the memory cache and the buffer. So we'd like to keep the page that will be used. So at the moment, we'd like to see the future, whether that will be used near soon. Okay, for example, in this case, we are going to use the same reference string with the full page frame. Obviously, the first full will be the page fault. No way to avoid this one. There is a way, actually. Sometimes the operating system, like the Windows, actually criticize a lot. It's very slow sometimes to start the program. So they sometimes preload some of the pages to the memory. Okay, then even though user does not start the program, some of the kernel or the system application started loaded into the memory, preloaded. Okay, as a background. So anyways, at this time we can avoid the page fault 1, 2, 3, 4. At this time, the 1 will be the reused reference, no problem. 2 will be reference. 5, there's no 5. We need to decide the victim page. In the first in, first out, 1 is the oldest one, so 1 will be replaced. But in the optimal algorithm, we'd like to see the future. Future means at this moment, C, next, 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 next. 1 will be used the next instruction. 2 will be used the next, next. 3 will be used the next, next, next. And 4 will be last one. Okay? So which means, which one should be in the memory? The 1, 2, 3. And the 4 has the last chance to be used. So 4 will be replaced by the 5, then the page 40. Then 1 reference this, 2 reference this, 3 reference this, and once again 4. So among this one, so we have only the 5 in future, but if we have the more page, the reference string, we can consider the other, but here, so you can replace any of this. You can consider the tie break, the algorithm as the first in first out. It doesn't matter anyway. So it will be page 40. Okay. So optimal is the ideal case. So it's the best performance for the page replacement. So it's always the best performance, which means less the page fault. Problem? We don't know the future. That is the problem. But nowadays, we estimate or predict the future. So computer system is not arbitrary to read the data. Mostly there are patterns to read the data. Or program itself is how many different instructions? It's not too many. Okay, we have the instruction is depending on the CPU 50 to 100. So, but not all of them are used. Some of so when we read the memory to memory, then the save to the memory to either register to register, then register to the memory. There are patterns. So if we can find such a pattern or the set of instruction working together, then we can pretty much estimate such a future. So optimal algorithm still being used in the memory replacement algorithm. Okay, so you can practice with another. So we are using the 2 reference string, but I'm not going to practice for the second one. So you are able to check the practice at home before your final exam. Okay, I mentioned many times. So definitely it will be the final exam. Okay, the next one is because anyway we cannot see the future, even though we can estimate what we can predict. So practically we can take a look back the past, because if we see the past, if some of them are used a lot, there might be higher chance to be reused. Somebody said if not used a lot long, think about the. So do you like the casino? No? So have you ever been to Las Vegas or the casino? No? So even this summer and several weeks ago, I went to the Las Vegas because Las Vegas is one of the popular place for the conference because it's a cheap flight and a cheap hotel. So a lot of hosts actually like to host such a conference in the Las Vegas, and there are something to enjoy. But I'm not very good at such the gambling or other thing. But the only thing I can play is roulette. Have you ever played the roulette? Roulette is the simple, just the even number or odd number, or red or white, so it's a very simple. You can bet. Okay, then. Usually, if you go to the casino in the roulette area, so there is a kind of the screen or something, the bar to show the last, the 10 or the 15, the number. Then if you see the 10, 20, 10, whatever, the even number only, then you believe that there might be higher chance for the odd number next. Does it work?
Maybe. No, it doesn't work.
Maybe.
It doesn't impact it.
From mathematics point of view, there's no relation. It's an independent event, which means it's still half and half. Okay? So, but people usually believe that. So sometimes it works. So even though you have the past, but this is not independent event. It's not random. Okay? there might be the one instruction to next instruction, they are usually related. So which means that there might be the existing pattern in the past. So one of the simplest way to characterize such a pattern is which one is near the leastly used, which one is the mostly used one. Okay, so how do we know? So for example, the 1, 2, 3, 4, then the 1, 2 is okay so far. But when we decide the victim page for the 5, so first in, first out, we will consider all this one. The optimal algorithm see the future, the 4 will be the victim. But using the LRU algorithm, least recently used algorithm consider when the data is used in the cache. So for example, 1 is used when? This time. Not this. This is entrance. But the reuse this time. 1 is the 2 times log back. The 2 is used just before. There might be higher chance to be reused. Okay? And what about the 3? 3 is accessed this time. 1, 2, 3, 4 times back. And then 4 is used 3 times log back. So which one is the least used?
3.
So 3. So we are going to replace the 3 by the 5. So this is called the least recently used LRU algorithm, which is the most popular algorithm any type of the algorithm for caching. Okay. So if you are taking the database class, so database we talk about the buffer management. So most of the data should be loaded into the memory, then the user can read the data from the memory. Then how do we know where is the data? It's in the memory, it's in the hard disk, or how do we know? At that time, LRU algorithm used. Most of the such a cache used such a LRU algorithm. LRU algorithm is kind of a list. So think about the linked list algorithm that you learned in your data structure class. Do you remember that? One of the variants of the linked list is optimal version of the linked list. Whenever the data item is accessed, you can promote close to the root node, head node. Then the mostly used one will be the first, right? The least used one will be last one. So this is also another version of the LRU algorithm. So this is LRU algorithm, then keep going. So for example, in the 3. So there is no 3, 1, 2, 5, 4, so we need to decide the victim. 1 is used 2 times the back, 2 is used just before, and the 5 used here, and 4 used long time back. So 4 definitely victim. So we replace the 4 by the 3 and so on, and so on, and so on. So how many page fault? 8 page fault. It's better than first in, first out. Not better than optimal. Optimal is always the best one. So this is the LRU algorithm. So benefit is a reasonably good performance and makes sense. Okay. So but it's even though not better than the optimal, but it's practically it's possible. Problem: more page fault than the optimal, but optimal is ideal case. So it's better than the other. Yes.
You need to keep data about every memory reference.
Which means
Previously.
so when it's accessed, how do you know? This time I need to check the 1 is 1, 2 times log back. 2 is just before, 5 is here, 4 is here.
Space complex.
If you have the millions of pages, you need to take millions of them, each of them, when is last time accessed. So for the algorithm itself, makes sense. But for the implementation, it's not that simple. You should have the space, and you should have a lot of computation to manage. So this one of the data, I'm going to introduce 2 approaches, but there are many other variations to implement the LRU algorithm. So one of them is using the counter. Counter, what is a counter? Do you remember the computer? Actually, does not have the real time. So how does the computer show the real time, like the 10 a.m. or 9 a.m., January 1st, whatever? How? It has just a counter, okay, instruction, okay? counter, that is the exact, the period, the time actually is implemented by the cycle. Then it's an electronic signal. Then it's the same as the real, so you can calculate the real time 1 second, then calculate the real time from January 1st, the 1970, January 1st. Then computer can calculate. So counter is actually the time, okay, the signal to be used for the time. So we can, it doesn't have to be the real time. Along the time, we can just a certain period time count how many of the, I said the time slot, okay? So how many period, how many round. What we want to is which one is the oldest one, which one is the nearest one to that has been accessed. So for example, this time for each pages, we will consider the counter. So every the time slot change, we will add up. So for example, here 1. This one is the increase by 1 and start to 1, and this time increase by 1, 3 by 1, so new one, the 1, and so on. So 4, 3, 2, 1, and this one is access reference. So reset because it's access. So reset new like the new one. 1 increase by 1, increase by 1. Increase. So this is along the time. We do not have the 2-dimensional array, so we will manage the 1-dimensional array. But still, if we have the more number of page frame, it will be huge, and also a lot of calculation. So we can keep. So at this moment, we need to decide the victim. Okay, like this one. So which one will be the victim? Highest number. The counter, we can just select. But for the calculation, it still takes a time. It's an overhead. So this is counter to address that problem. Another approach is using stack. We are not going to use a stack as it is slightly changed version of the stack. Okay, for example, so this is a stack. In case we have the 4-page frame, we will manage the 6, the node, the stack. This is a stack. This is the top. This is the bottom. Okay, so this is the top, this is the bottom. Don't be confused. We are going to start here. The put, like this one. And the pop. So, for example, if the 1 is with here, and the 2, 3, for there might be no problem. Then, if the reference, so 1 is referenced here. So then, at this time, the bottom one will be the change the position. Okay, so we can change the position and the move. Actually, in the real implementation, we don't have to change the copy and paste. Just change the pointer. Okay, we can just change the pointer. This is illustration purpose. So then the 1, 4, 3, 2. Then 2 is success. Then the 2 will be top and move down. So then once we decide the victim, so first insert the 5. Then which one will be the victim?
The last.
The last one, bottom one. This is the oldest one. Okay, similar as what? Optimize the linked list. It's a similar, mostly same as idea as the optimize the linked list and so on. So this is the stack implementation. Still, if you have the millions of page frame, this stack size will be huge. It takes a time. Okay. So it's simpler than the counter. Counter, you need to manage at least several byte, or the 1 byte, or the several byte for each pages. But this one, we can have just fix the size of the stack. But it will be still overhead. Another algorithm is error approximation. So this is the summary of the last 2 algorithms. The error approximation is we are not going to consider for example, this time the problem of the counter is if the 1 is accessed frequently, you need to manage all the time. Okay, the more page frame you have, the longer time you need to manage. But we don't have to worry about the 1 hour before, 2 hours before data. Usually, the last few seconds or last few minutes the how much access we used. So that means we are not going to consider the all of them. Instead, the last, the number of the time slot. So then the which can be referred the minute by the, if you think about the free frame. So first time they set the 0, 0, 0, 0 for each the free space, like the free block in the file system, or free frame the page. Similarly, so we are going to manage such a reference bit along the time for each the pages. So let's say that we are going to manage 1, 2, 3, 4, 5, 6, 7, 8. The first is set the initialized as 0. Then the, for example, this one. This each pages has their own reference bit, like the 8-bit this time. Then, if one is accessed, it will be set as 1. Most significant bit will be changed by 1. 1 means reference. Then, next time slot, moving to the next, then you shift. Shift it, how can you shift the bit? Most of the CPU provide instruction to shift. So which means it's very fast. Okay? So you don't have to do the programming code. It's mostly the instruction level. So hardware level. So it's a 0, 1. Then what about the second frame? It will be 1, 0, 0, 0, 0, 0, 0. Then the next, whenever you move to the next time slot, shift to right. So this will be 0, 1, 0, 1, and next one is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? And keep going. For example, at this moment, if 1 is accessed, this one will be changed to 1, 0, 0, 1, like this. Then, how do you decide the victim pages? So, in this example,
Smallest number.
so in this example, we have
Smallest number.
the page frame number 0, 1, 2, 3. Which one will be the victim page?
3.
Number
3.
3. Because what is the idea? If the value is lower, okay? Because we update the most significant bit for what? Reference. Which means highest number means least, the recently accessed. Okay? The lowest number, least recently used one. So this will be the victim page. And how do you calculate this one? There is an instruction also. The most of CPU provide the instruction with how many the 0 then at the most significant bit part. So highest number of 0. So this in this case 1, 2, 3, 4, 5 0. And this one 0. And this one has the 1 0. This one is a 0. So which means this will be the victim page. You can calculate. But the problem benefit comparing to this one, it will manage only